think about this.
Thank you very much. Hi everyone. So today I would like to talk to you about implementing the parallel discrete event simulator with the Erlang language. So what's the outline? I will briefly introduce you to the discrete event simulation paradigm. I don't know if you're familiar or not with this paradigm, but I will introduce to you. Then just bits and pieces of Erlang, the architecture of the Erlang time warp simulator, that is the core of the paper, how we test it, the results, and conclusion of future works. So let's start with the definition. What is a simulation? Professor Fujimoto said that a computer simulation is a computation that models the behavior of some or real imaginary system over time. So that's really generic. So we can dig up a bit more and say that a simulation is basically is structured in two layers. One is the simulator layer, and one is the simulated model. So the simulated model is the first one, and basically it offers a formalism to abstract and express your system, to simulate. The simulator is a general environment that helps you to manage and perform simulation. So let's keep these two layers in mind because we will have another slide as well. So what is a discrete event simulation? It is a paradigm to perform simulation in which we have four main keystones. The first one is the notion of state. It is basically a set of variables that represents your system in all the evolution of the simulation. An event is a change in one or more of the variables that belongs to the state, and it happens in a predefined distant instant of time. So we'll have an event that will be coupled with a timestamp. Then the evolution of the simulation is a sequence of events, and the time advanced by discrete steps that are basically the timestamp of the events. So that's the name, discrete event simulation. So here we are our two layers. We can instance the two general layers for sequential discrete event simulation. In the simulated model, we will have again a set of variables and a set of event handlers. So an event handler is a function that takes an event and does some changes to the state variables. And then in the simulator we will have an event list with the processed and unprocessed event, and then a global clock that will go forward, and it represents the going forward of the simulation. So as you can imagine, a discrete event simulation must process events in a non-decreasing time ordering. Otherwise, we will have some issues. So this is a really simple example. Imagine that we want to simulate the traffic flow from two airports, the Guglielmo Marconi, that is in Bologna, where I come from, and the other one is the Copenhagen airport. So we will have for each airport two state variables, the aircraft in the air and the aircraft on the ground, and two kinds of event, that is the departure of an aircraft and landing of an aircraft. This is a very basic example just to show you what is a discrete event simulation. So imagine also that we have to simulate two flights, one that departs from Copenhagen to Bologna at 10 a.m. and lands in 12:30, and then another one that departs from Bologna to Copenhagen, departs at 9 and lands at 11:30. As you can see, events are overlapped, so this is important because we have to find a way to serialize those events, and this is the thing that will do the simulator. So obviously the starting events will be the departure events. The first one is the departure of the the Alitalia flight, exactly. And we have the processed event in the bottom. We have the event processed at 9 a.m. The global clock in the upper right corner is 9 a.m., so it has advanced by one step. You can see the state variables of the airport, and we have two events processed. The first one is the departure of the Scandinavian Airlines flight, and then we have another event, the landing of the Alitalia flight to Kastrup Airport. So, as you can see, that event has been created by an handler that has processed the departure event at 9 a.m. and it has generated another event, that is the landing. Then, this is the Kastrup Airport, global clock is 10 a.m. and we will have two events processed and two events processed. Again, another event pops out, that is the 12:30 Scandinavian Airlines landing. As you can see, global clock is 10 a.m. We go forward, 11:30, and we have three events processed and one to process, and then the end of the simulation. So, as you can see, events have been serialized in a non-decreasing time ordering, and this is important. So, I hope you got some bits and pieces of the discrete event simulation. As you can see, is a very simple and elegant way to perform simulations, and the simulator does all the work for you. The only thing is, if you want to manage and simulate big and complex systems, as you can imagine, 100, 1,000 airports with a lot of flights, it's not feasible on one single execution unit because it will take ages to complete. So what's the solution? We are going parallel, and then we will have multiple instances of the simulator running at the same time, communicating through message passing, as you can imagine. We have to introduce a little bit of notation. So a logical process will be an instance of the simulator, basically. So again, we have the two layers of the simulation. We have the simulator and the simulated model. So in the simulated model, we have to partition the original sequential model into more than one pieces, and each pieces will be run into a separate simulator. So for our example, maybe one airport goes to one simulator and the other airport goes to another simulator. But this is not so straightforward for all the models. The simulator has to perform local consistency and global consistency. So what does it mean, local consistency? Is guaranteeing that each instance of the simulator process event in a non-decreasing time ordering. And if we have that, we can guarantee that we will have global consistency. That basically means that the simulation will yield the same result as a sequential one. But how do we ensure local consistency? As you can imagine, it's really, really difficult because logical process or simulator instance can go forward at different speed and with different workload. So we have to use a synchronization algorithm. In the field, we have three main families: the time-stepped, conservative, and optimistic. Time-stepped approach is basically partition the entire sequence of the entire history of the simulation in fixed amount of a fixed step of a fixed amount of time, and then at the end of each step you will synchronize every agent of the simulation. The conservative approach is basically it forces a logical process to process an event only if it has the assurance that that event that he will not receive an event with a lower timestamp than the actual. The optimistic one is the as you can maybe the more scalable, because it lets simulators to go forward without any restriction, and if something happens, so if a struggler event arrives to a simulator instance, there will be a rollback of the entire system to a safe place. That is a point in the history of the simulation that everything is consistent. So we choose to implement the time warp synchronization. We have planned to, that is, the time warp synchronization algorithm is the most valuable optimistic synchronization algorithm. We are planning to do it for the conservative approach too. Again, there is no attempt to preserve consistency. The important part is if a causal violation of the events occurs, then a rollback is needed. So this is really complicated algorithm. I'm not going to say more. If you want, you can go to the paper, because it would take, I think, 1 hour only to explain the time warp. And so let's introduce Erlang, because we implemented the time warp in Erlang. So it's Erlang has 20+ years of research and development in the shoulder. It's functional and concurrent. So it implements the actor model. Basically, the Erlang virtual machine has this notion of Erlang thread, that is user-level threads, and they are the first-class object of the language, and those threads are mapped to Erlang function, and each Erlang function will communicate to each other using message processing primitives that are embedded directly in the language. So this is the architecture of the Erlang time warp for a single host. As you can see, there is the operating system layer, the Erlang VM, and then the Erlang time warp framework, that is our library. It offers some useful tools for the logical process instances of the simulator. So in this example, we have 8 instances of the simulator running in parallel on a single host. And then this is the multiple host scenario. So as you can see, we have the same architecture replicated to hosts, but what we exploited a function of the Erlang VM that basically permits to join multiple virtual machines on a single cluster. So each virtual machine will know the network topology of the cluster and outreach by means of IP address and port other virtual machines. Then, using this functionality, we build a library that basically abstracts the virtual machine cluster topology to the logical process. So from a logical process point of view, communicating to another simulator instance on the same machine or on another host is basically the same thing. It will use the same primitives and the same abstraction layer. So how we tested this simulator? This is the a version of the parallel load model. We have the concept of entity. An entity is the smallest amount of the smallest unit of execution for a simulation. It's a concept that resides on the simulated model layer, and this permits us to map multiple entities to a single logical process. This is something that has to be programmed by a simulator user, the user of the simulation. So it's nothing that resides in the simulator layer. So the simulator does not know about the entities. So again, the model is basically a graph, a strongly connected graph of entities. Those entities will communicate each other, exchanging events. In the beginning, we will have a fixed amount of entities, that is a parameter of the model. that will start the communication. In this case, we have the 50% of the entities that start the simulation, sending events, selecting the target randomly using a uniform distribution, and applying a timestamp that is a result of an exponential random generation, pseudo-random generation function with means of 5. So in this case, entity 6 is sending an event with timestamp 10 to entity 2, the same entity 5 to entity 3, entity 1 to entity 4. Then the entities will respond to that event. In this case, entity 2, for example, will send an event to entity 6 using the last timestamp that it has received, plus another random amount of time. And this goes further until we reach a global maximum time that is the end of the simulation. So this is the standard test for the time warp algorithm, because it's I don't know how to say homogenic work. So every entity does the same amount of work, and you can test in both shared memory and distributed memory architecture the effect of latency. So this is the hardware-software environment. This should be a single table, but I split it into two parts just to be clear. The first line is the shared memory architecture. We use the Intel i7 with 4 physical core and with hyperthreading. And then Cassandra, Cerberus, and Cernobot are 3 machines connected into a cluster with gigabit Ethernet. And as you can see, this is not an HPC, obviously. And the hosts are not the same. So we have different processor, different velocity, and as you can see, Cassandra and Cerberus has 2 physical cores with hyperthreading. Cernobot has 4 physical cores with no hyperthreading. So we wanted to test the effect of the latency and the effect of different hardware for our simulator. So those are the tests. For the shared memory, we tested from 1 to 8 logical process on the same machine. We formed a distributed memory from 1 to 6. The number of entities are 840 until 3,360. So 840 is the minimum common multiple for every from every number of LP. The Evin density is basically the number of starting entities. In this case, it's 50%. And the workload is a synthetic function that each entity will execute before generating an event. This is to prevent the simulation to be I/O bound and more CPU bound. And you can add more or less floating point operation, and you can see the results. So this is the speed up results for the shared memory architecture. I recall that it was an Intel i7 with 4 physical core with hyperthreading. So we have 4 we call physical core and logical cores. Logical cores are the hyperthreading ones. As you can see, we have the workload is 10,000 floating point operation each time an entity is processing an event. So as you can see, until we have until we reach 4 logical processes that are the maximum number of available CPUs, we will have almost linear scalability. Then we will have we have a step down, because in the 5 case we will have the interleaving between processes, and so this is not good for the time warp algorithm. This is the workload for the distributed memory environment. As you can see, results are not so so happy, and it's a poor scalability. So we have identified 2 main problems. The first one is that the time warp algorithm is really sensible to latency. That in this case we have introduced latency to the system, and then there's no way to group entities at runtime that are working together on the same machine. So we can group entities with same with high interaction rate to the same logical process in order to prevent the effect of latency. But this is a thing that we are planning to do in the future. So Erlang is a really good language to build parallel and distributed simulations, and in this case the results of this work is that we have a single library that permits us to write code both from shared memory and distributed memory at the same time without any sort of changing in the code when you switch to the architecture. And that's really good. We have built the same. We have implemented the time warp algorithm in Go, only for the shared memory architecture, and until now it's really faster than Erlang, but this is imperative versus functional, and we can talk about 30 minutes more, but so this is the results. And as I said, time warp algorithm does not scale very well with network latency. Future work. Redesign of the library using the Erlang TW framework, just to follow standards, and study auto-tuning the virtual machine to improve the performances. These tests have been executed on the standard Erlang virtual machine without any sort of tricks or changing of their parameters, and as I said, conservative synchronization algorithm just to have a comparison. And then we will hopefully try this simulator on an HPC architecture, trying to obtain a decent scalability. So that's it.
All right, let's take this. Questions?
Sorry for my bad Italian, for my bad.
So how do you handle rollback? Do you take snapshots?
It would take us, I think, 30 minutes only to explain everything, but basically you will find all the events that have been to roll back in a single logical process. Then you send those events back to the other logical process in order to say to them, hey, those events will have to be rolled back. So
right, but just in terms of a local state, are you just saving copies periodically and then bumping back to them when you have to do a rollback?
Yeah.
So
it's more complicated, but you have to have everything in memory, and then you have a thing that is the global virtual time, that basically it gives you the lowest bound of the possible rollback, so the minimum timestamp that a rollback can reach, and then you can free all the events that have timestamp lower than this timestamp.
So do you think, or how hard do you think it would be to integrate reverse computation or something that reduces the memory requirements within your framework?
What do you mean with the reverse computation? I'm sorry.
So rather than saving old states, just being able to reverse the operations that led from the old ones.
Okay. Yeah, there are some papers. You can do this in some cases, or in other you can't. But it has been studied. There is this.
Right.
So for this is a prototype. So we choose to implement the fastest way.
Okay, do you think it would take a lot of changes to your implementation to do that?
Yeah.
Okay.
I was just wondering whether you compared your simulator written in Erlang with the other simulators written in Erlang. I mean, did you compare the performance of their approach with your time Warp?
So there are other simulators written in Erlang, but they are not implementing the discrete event paradigm. So we can take other simulator, but they won't yield the same results because they implement different paradigm of simulation. That's basically. It should be unique in this in the field. So it should be.
I've got a couple small questions. First is, what is Erlang OTP?
Yeah, it's a framework. It's very famous in the Erlang community, and basically it offers a thing called behaviors that has it permits you to express things like servers or other things in a standard interface.
Thanks. And the OTP is online transaction processing, or what's?
No, it's I don't know now, but
Oh, okay. It's lost to history. And finally, for the synthetic benchmark you presented, was there no locality in terms of any entity was equally likely to message any other entity?
Exactly, yeah. This is the problem. So there have been a lot of studies in grouping together entities on the same highly interactive entities that interact frequently each other on the same logical process in order to prevent latency of the network. But again, this is a thing that we will do in the future.
Great, well, we look forward to it. Thanks. Let's thank the speaker again.